Guys, last time we talked about Gauss's law, and we said that Gauss's law actually calculates the flux. It says that the flux, the electric flux, equal to the integration over a closed surface for E dot ds, which is also equal to the charge inside Gauss's surface divided by epsilon zero. And this is Gauss's law. Gauss's law, if we have symmetry over the charge distribution, then it will make our life much easier, because it will save a lot of time in getting the electric field everywhere. And since we're talking about integration of a closed surface for E dot ds, then if we talk about that shape, the integration over a closed surface for that shape, which is the surface area of that shape, which is going to be, if this is A and that's B and this is C, guys, this is A, B, C. So the integration over ds for that shape is going to be AB times 2, AB times 2. This is the area of the base and the top, and those two sides, it's going to be 2BC plus 2AC, and this is the area, the integration over that closed surface. And that's what we mean by closed surface. If we're talking about cylinder, and that's what we have shown last time, then the integration over a closed surface for that cylinder, that's the area of the top and the area of the bottom, which is by r squared times 2, plus the area of that round shape, which is 2 by r times l. And if we're talking about sphere, then the area of a sphere, that's 4 by r squared. So the integration over ds for the sphere, that's 4 by r squared. Now we'll try to find the electric field from a charged sphere. So if we have a sphere, solid sphere, and if that solid sphere has some charge Q distributed all over the sphere, inside and out, and we need to find the electric field everywhere from that sphere. How did you know that? No, the charge can be on the sphere, inside the sphere itself, inside the volume, and it can be only on the surface. That depends on the type of the sphere, and we'll get into that in a minute. Okay? For now, let's assume that we have a sphere, and we know, Sharif, we know that the charge is distributed everywhere, inside the sphere and on the surface. And we need to find the the electric field everywhere from that sphere.
Everywhere
from the sphere, everywhere. So I'm going to leave that, go to the board for a minute. This is the sphere. It has a charge Q on it, and we need to find the electric field everywhere. And when I mean everywhere, I mean inside the sphere and outside the sphere. What is the electric field inside the sphere, and what is the electric field outside the sphere? Outside the sphere, the electric field, calculating the electric field is much easier. So I will start by calculating the electric field outside the sphere. So at that point, which is at a distance r, from the center of the sphere, we need to find the electric field. So to do this, simply we're going to apply Gauss's law. But before we apply Gauss's law, we draw what we call the Gauss's surface. And Gauss's surface, that point has to be on the surface of Gauss's surface. Now we have a spherical symmetry, and it makes sense that we choose Gauss's surface to be a sphere as well. Since the charge is on a sphere, our Gauss's surface has to have the same symmetry. So it has to be a sphere as well. So I'm going to draw a sphere. That's a virtual sphere. And that sphere, that's our Gauss's surface. This is step number 1. Step number 2, I'm going to apply Gauss's law. And Gauss's law says that the electric field, the integration of E dot ds will equal to Q inside Gauss's surface. divided by epsilon 0. If we look at Gauss's surface, the electric field, this is one of the good things about Gauss's surface. The electric field along Gauss's surface is constant. It's the same everywhere.
So radius is constant?
Yes, of course. This is R, this is R, this is R. Yes. So the electric field on the sphere is constant. And if the electric field on the sphere is constant, then the electric field goes out of the integration because it's constant. So we end up having the electric field dot the integration of a closed surface for ds equal Q enclosed divided by epsilon 0. What is the integration of ds for a sphere? It's the area, the surface area of the sphere. So that's going to be E dot the surface area of the sphere. Gauss's sphere. Gauss's sphere. The area of Gauss's sphere. Okay? Which is equal to Q enclosed divided by epsilon 0. Now that dot product, what is the direction of the electric field from that sphere? It's always out of the charge. This is the charge, so this is the direction of the electric field. This is the direction of the electric field. This is the direction of the electric field. What is the direction of the area? You draw a perpendicular. This is the area at that point. At that point, this is the perpendicular to the area. So the electric field and the area are along the same direction for that sphere. Electric field and the area are along the same direction. So E dot A, it's just E times A. That's dot product. So E times A times cosine the angle between them, and the angle between them is 0.
Okay, طب دكتور لو كان مثلا في كيس تاني مش في لو كان ريكتانجل او
We'll talk about it. We'll study about so many cases. Okay, guys. So E dot A in that case will be just E times the area, and the area, as you said a minute ago, that's 4 pi r squared. Now, what is the charge inside Gauss's surface? Now, if I put my hands on Gauss's surface, look inside my hand. Between my two arms, what is the charge inside Gauss's surface? It's the charge on the sphere. That's the Q. That's the total charge Q. So the charge on Gauss's surface now, this is the total charge Q. Can you calculate the electric field? So the electric field outside the sphere will equal to 1 over 4 by epsilon 0 Q over r squared. Okay, guys? Okay, guys? So the electric field at any point outside the sphere equal to 1 over 4 pi epsilon 0 Q divided by r squared, where r is the distance between the center of the charged sphere and the point that you're trying to find the electric field at. So that's easy. It's exactly look like the formula that we know for the electric field from a point charge. So actually outside the sphere, the charge will look as if it is all concentrated inside the center of that sphere. The charge on the sphere will look as if it is all concentrated inside the center of the sphere. That is the electric field outside. Good, that's one.
Doctor, can you do it from the beginning, A Q over R squared, because it's point.
But the charge, we use that formula E equal K Q over R squared if the charge is point charge. But this is not a point charge. But we have proven now then that it actually, if you are trying to find the electric field outside the sphere, it will look as if it is all concentrated inside the sphere.
So we can use this formula.
Yes, yes.
And we don't need to prove that it's,
Look at the proof. It's so simple. It's so easy. Okay, what else?
okay, it's ds.
What's ds? This is the integration. This is the integration that I was talking to you about a minute ago.
Okay.
backspace. The integration over a small, you choose a part of the surface of that sphere and you integrate it all over that whole surface. So the integration of ds, this is the total area of the surface of the sphere, that's 4 pi r squared. So that integration for the sphere, this is 4 pi r squared. That's it. Okay? Okay? There's no example. Those are the 3 examples that I can give for surface area. In here I said that if E is constant, then the integration will be only over the surface. The integration over a surface element, this is the total surface of the shape, whatever the shape is. So the integration of a surface element in here for that shape is going to be the total surface area of that shape. The integration over a small surface area element on that cylinder will be the total surface of that cylinder, which is that. Same goes for the sphere. Okay? Ask. Epsilon 0? Oh, E outside of the sphere. That's what I mean by E out. Okay, guys? Yes.
When you said to consider the charge as a point in the center, is this only for sphere?
For solid sphere.
Any other shape? No.
We'll find out. So for a solid sphere, if it has a uniform distribution of its charges, and you're trying to find the electric field outside of the sphere, then you can look at that sphere as if the charge is concentrated in the center. Okay? Yes.
In the exam, I have to derive the proof or just put the rule?
Are you going to memorize the rule? Okay, in the exam I give you a formula sheet. You can put those formula sheet only in your exam paper, in your solution. Other than that, if you need any other formula, you have to prove it. But this is the beauty of Gauss's law. It makes our life much, much easier. Do you know how long it will take to prove that for you guys if we use Coulomb's law? At least 45 minutes. Because you have to do an integration over x, y, and z. And if you do it in a Cartesian coordinate system, it's not that easy. You have to transform that into spherical coordinate system and solve the integration over 3 coordinates, r, theta, and phi. 2 angles and r. So it's not an easy integration to do it. So what you do is you choose an element inside the sphere, and you say that this element has a charge dq. Then find the electric field from that element outside the sphere, then integrate all over the sphere. And this is integration in 3 dimensions. It's not an easy integration to do. It's doable. People have done it before, but that in 2 steps, you get the electric field using Gauss's law. That's why we say that Gauss's law makes our life much, much easier than Coulomb's law. Right? So, and do not think about the exam. Do you understand that part? Good. This is what I want.
So we don't need the proofs anymore?
I didn't say that. I did not say that. I said if we have symmetry, then we can use Gauss's law because it makes our life much easier than Coulomb's law. But sometimes we have to use Coulomb's law because we do not have that symmetry. Okay? Okay, now we solved the first part. Second part is how to find the electric field inside the sphere. So inside the sphere, we'll go back to the sphere. It has a charge Q, and it has a radius. So the sphere has a charge Q, and it has a radius R, and we need to find the electric field at any point inside that sphere. So I'm going to say that we want to find the electric field at that point, at a small radius, at R, small r, at a radius small r. That's where we need to find the electric field now. What I'm going to do is exactly do what I have done in the other case when we were trying to find the electric field outside the sphere. We'll draw Gauss's sphere. That's an virtual sphere. We'll write Gauss's law. Once more, the electric field on Gauss's surface is constant, so it goes out of the integration. Now, what is that integration? So it's E times 4 by small r squared. R here is the radius of Gauss's surface.
How did you get that?
Which one? Which one of them?
The 4 power squared?
That integration.
Okay, what is the area of the circle?
That's not a circle.
The T is sorry.
4 pi r squared.
That's the reaction integrated.
No. You don't have to integrate. What I'm saying that if you have a sphere, and you divide it, if you divide that sphere into small parts, each part has an area of ds, and if you integrate all over that sphere, or in other words, if you add up all those ds's, you end up having 4 by r squared. Okay? Equals to q enclosed divided by epsilon 0. This should equal to q enclosed divided by epsilon 0. What is the charge inside Gauss's surface? Is it q? Is it capital Q? What is the charge on the whole sphere? Capital Q, right? What is the charge on Gauss's surface? Part of it, not all of it. Yes, we have to divide it as a ratio between the two volumes. Exactly.
Why is it called not all of it?
Because we're trying to find the charge inside Gauss's surface. Only the charge inside Gauss's surface, not the charge inside the whole sphere.
Isn't it equally distributed inside the sphere?
Which means that we have some charges here outside of Gauss's surface, which we did not include inside Gauss's surface. So the charge inside Gauss's surface should be less than the total charge Q. Okay?
I thought charges only were on the surface of any sphere, any object. I didn't think there was inside the core of the...
No, it's in that case that you came in late, right?
Yeah.
Yeah, I said on that specific sphere, the charge is distributed everywhere, in and out.
But normally it's only out?
I'll answer that in like 5 to 10 minutes.
But Q remains constant for its large sphere.
It's uniformly distributed. Yes, Q is the same. It's not going to change.
Watching vector sphere we measure.
Yes, and the green one, that's Gauss's sphere, which is the virtual sphere. We use it only to apply Gauss's law. And the point that we need to find the electric field at should be on the surface of Gauss's sphere. What else? So now we have to calculate that Q enclosed. So I'm going to say that if we have the total charge Q, is distributed all over the volume of that sphere, which has a volume of 4 over 3 pi capital R cubed. Q enclosed is uniformly distributed over Gauss's surface. I'm just stating facts. I did not do any calculation yet. I said the total charge Q is uniformly distributed all over the volume of the red sphere, the whole sphere, the real sphere that we have. While the charge Q enclosed is the charge inside Gauss's surface. So it's uniformly distributed over Gauss's surface. Can we calculate Q? This times that should equal to this times that. So if I say Q enclosed equal to Q times 4 over 3 pi r cubed divided by 4 over 3 pi r cubed. Do you remember what is that? No. First of all, it does not have the units of electric field. This is over r cubed and r squared. So it's not an electric field. That's a charge density. That's the volume charge density. It's the total charge on the sphere divided by the total volume of the sphere, and we call that before charge density. This is the charge density. So this can be written as Q enclosed will equal to rho, which is the charge density, and rho again equal Q divided by volume times the volume of Gauss's surface times the volume of Gauss's surface. So now we know what is Q enclosed. Okay guys? So I'm going to replace Q enclosed by its value. Q times 4 over 3 by r cubed divided by 4 over 3 pi r cubed, and I'm not going to forget the epsilon 0 because it's Q enclosed. Guys, because it's Q enclosed divided by epsilon 0. Okay guys? Ask. Oh, I will do that right now. I just wanted you to observe what I'm doing first before I go and cancel terms. Yes, Abdullah.
Charge on Gauss's surface, you mean the charge
inside Gauss's surface.
inside.
Mhm.
The EV represents the electric field.
That's the electric field. That's the vector. Yes, that's the electric field.
Inside this field.
No, at the point that we need to find the electric field at that point. At any point along that surface, along Gauss's surface. Yes, and the formula is still there. It has to be on Gauss's surface. That point has to be on Gauss's surface. Yes, what else? Ala, ask. Amr. Guys, okay? Should we cancel out those terms? In red? Then? Yeah, but I didn't want to. It's the same thing. You know, I did not use that formula. I used that. Same thing. So, N. I mean N inside the sphere. Inside, at any point inside that sphere equals to 1 over 4 pi epsilon, and that's the 4 pi, and that's the epsilon, times Q r small over r cubed. I did it that way for a reason. I will show it to you in a minute. But that's that electric field inside the sphere. So if you have a sphere, solid sphere, and you have charge uniformly distributed all over the sphere, and you need to find the electric field in and out of that sphere, inside the sphere, the electric field is going to be given by that equation. Outside the sphere, it's going to be given by that red equation.
Outside the sphere, it depends on the small r. So it
course.
will be different
Of course.
in different points.
Same thing goes in here. R, again, R, small r, either here or here. Small r means the distance from the center to the point that you need to find the electric field at.
Who decides on this r? You mean this r?
The problem?
The problem.
I asked you to find the electric field at a distance. If the r is 5 centimeter, r capital, 5 centimeter, I asked you to find the electric field at 2 centimeter and at 7 centimeter. Then you cannot use the same formula. Use that for out of the sphere. Actually, you prove it. And we use that for inside the sphere. Actually, also you prove it. But can we draw this? I want to draw that graph. Okay, I'll answer that first. Sharif, you got confused between that R and that R? R is the radius of the sphere. R small is the radius where you are trying to find, it's the distance between the center of the sphere and the point that you're trying to find the electric field at.
دكتور ما احنا هنا we used R small despite انها كانت the radius كان طالع بره اصلا.
Yes? If it bother you, I call that R. If it really bother you, I'm going to call that distance D. Okay? And then this is going to be D. I use the same symbol for two different things. It's a distance. And actually it's for the same thing. It's a distance from the center of the sphere till the point that you're trying to find the electric field at. And it doesn't matter if it's inside or outside the sphere. R small is the distance between the center of the sphere, that the point that you're trying to find the electric field at. Okay? And R capital, that's the radius of the sphere. Okay.
Okay. عرفت ان الشارجز are equally distributed.
Hmm.
Okay. طبعا كل ما الار decrease الار small will decrease
Hmm.
electric charge will decrease.
Of course.
ازاي يكون distributed وفي نفس الوقت الشارجز will not be equal.
I mean, each unit volume has the same amount of charge.
Okay.
That's why we do this. Each unit volume has the same amount of charge, has rho. So if you have a volume of blah blah blah, you get the charge on it.
Doctor, now we can use these two formulas for every shape of the sphere, right?
Yes and no. You can use those two to find the electric field in and out of a sphere that has a uniform distribution of charges, a solid sphere. Not the, you can use those two formulas for any solid sphere that has a uniform distribution of charges. But do not write that here. You don't need it. على
So if you take spheres او shapes يعني.
Yeah, we'll take a shell now. I'll study if we have a shell like a football shell and has a charge on it, how to find the electric field. And if I will teach you also if we have a sphere in the center and around it there is a concentric shell, how to find the electric field everywhere.
طب يبقى constant الشارج.
What's the constant charge?
الشارج يبقى constant يعني constant جوه equal distributed.
Oh, it has to be equal distributed for now. At least for that lecture, yes. Okay, guys? Yes. Nothing. I got Q enclosed. I put it in here. That was Q enclosed over epsilon 0. So I replaced Q enclosed by its value, and that's it. There's nothing.
We cannot use these two formulas unless we can.
You can use only if in the exam, this is about the exam again, which I hate to talk about. In the exam, you can use only the formulas in the formula sheet. Any other formula, you have to prove it.
ودول are they going to be provided in the formula sheet?
No.
Can we see the formulas?
If you memorize them and you put them, you do not get marks for that. And trust me, if you save time and we take more examples, it will be much easier for you. But if you keep wasting time asking about the exam, it's going to be hard for you to actually get it in the exam. So let's save the time. Okay? And so guys, I will answer the question that has a meaning to me. I'm going to write the formula for the electric field outside the sphere. That was equal to 1 over 4 pi epsilon 0 q over r square. This is for outside, and this is for inside the sphere. Okay, now I need to draw them. So what I'm going to do, this is a graph that represents the electric field with the distance r. At r equal to 0, what is the electric field? R equal to 0, that should be inside the sphere, so I should use that formula. Again, at r equal to 0, this point is located inside the sphere, so then I should use that formula. At r equal to 0, what's E? 0, good. Yeah. But at r equal to 0, this is definitely inside the sphere. Okay? Yeah. If you look at those two, all those quantities, those are constants. So the electric field is directly proportional to r. This is a straight line relationship. So r, electric field will increase as r increases till r equal to the radius of the sphere. Put r equal to r capital. What happens? Put r equal to r capitals. Do they all agree? Do they both agree? You get the same answer. So if you choose that or you choose that, there is no discontinuity in here. You get the same answer from the two equations. And outside the sphere, that's what happens. E proportional to 1 over r squared, and here E proportional to r. And that's the graph that represents to us the electric field everywhere from charged solid sphere. Sure. Again, what I'm doing now, I'm just drawing the electric field as a function of E. So I said at point r equal to 0, this is definitely inside the sphere. And so if you put r equal to 0, the electric field has to be 0. So the electric field is equal to 0. And if you look at that whole equation, everything here is constant except r. That's your variable in here. So E is directly proportional to r. This is a straight line relationship. So this is E is directly proportional to r. At r, if you need to find the electric field at the surface of the sphere, which formula should I use? Well, if the physics is correct, if you choose that or you choose that, you should get the same answer. So I'm going to choose that for now. And look, r equal to r capital. That formula will be 1 over 4 pi epsilon 0 q divided by r squared. If you use that equation and put r equal to r capital, you get the same equation, same answer. So at that point, this is the surface of the sphere. Then outside the sphere, we should apply that formula. We should apply that formula, which is electric field outside the sphere equal to some constant times 1 over r squared. It's inversely proportional to r squared. And this is the equation. And it makes sense. If you have a sphere, the electric field at your location, it's going to be stronger than the electric field at the end of the room. And that makes sense. The electric field closer to the surface of the sphere is stronger than far away. And it's also, let me finish, then I will take all the questions. The electric field inside the sphere increases as you take more charges into consideration. When you move from that point to that point, you include more charges. So they have more charges inside Gauss's surface, the stronger the electric field. till you include all the charges. So if you increase the distance trying to find the electric field, the electric field decays as 1 over r squared. شريف.
طب كده يا دكتور عمر الالكتريك فيلد هيبقى ايه؟
What r is infinity.
هو ار عماله بتجمع يعني
Yes.
الالكتريك فيلد بيقل لما ار تكمل تفضل تكبر لحد امتى بقى؟
Excuse me? E is not increasing. It decreases as 1 over r squared.
بس it will never reach zero.
It's at infinity. And what is infinity? It depends on the size of the sphere. So if the sphere is that big, then your location is infinity compared to the sphere. So at your location, we're not going to be able to measure electric field. Very, very, very small electric field that you can ignore it. So infinity, this is relative.
It doesn't make sense in this distance is infinity.
It makes sense. It makes sense. If you have an object that can move only 1 nanometer in his lifetime, then it will never reach you. This distance is infinity. It's all relative.
No, sir. It's easy to understand that inside the circle, as you move out, it increases.
You add more charges.
You add more
Yes.
charges.
Yes.
But why does it increase هنا curve r وهنا 1 over r squared?
Because
Mathematically, I understand.
Uh-huh.
Is there like a logical way to explain it?
because actually this is a uniform distribution. So you add more volume, you add more charge. This is one-to-one relationship between them. Outside it decays. You get further away from, this is what we call it, if you remember in high school, the inverse square law. Any radiation decays as 1 over r square with the distance. This goes for electric field, magnetic field, any type of radiation, radioactive radiation, anything, acoustic wave, acoustic radiation. That's the inverse square law. So actually this is nothing but the inverse square law.
طب يعني الأوبتيمال تشارج على السيرفيس اوف السي.
What do you mean by optimum charge? The maximum charge. Yes. If you take your Gauss's surface, just at the surface of the sphere, then this is the maximum charge that you can get. Okay, guys? Okay?
Now, Ms. Doctor, can you please repeat the part of the first part, proportion to R? I understood that out, okay, but the inside one.
Oh, okay. I said we need to find only the charge inside that green sphere, which is that green sphere that's Gauss's sphere.
Okay, I understood all this. The part that I didn't understood is E proportional to R. And,
E.
E proportional to R.
Oh, yeah. Look at this. 1 over 4 pi epsilon 0. Those are constants.
Yes.
Q is constant, doesn't change. Outside the sphere, Q is the same, it will not change. The radius of the sphere is not changing as well. So if you plug in the value, all of this will give you some constant. Call it, what's your name? Tariq. That whole constant is Tariq. I'm going to call it constant Tariq. So the electric field will equal constant Tariq times R. This is Y equal AX. That's why it goes into. That's what I said. All of those are just constants. They do not change. I mean by they do not change regardless of your choice of R. Those are constants. If you take R here or here or here, the charge on the sphere is Q. It's gonna remain Q. It's not gonna change. 4 pi epsilon is gonna stay as is. The radius of the sphere is not going to change because it's not expanding or shrinking. It's staying the same. Okay? Good. I should add now that the only material that the charge can be uniformly distributed all over the volume of the material is non-conducting material. Sometimes we call it dielectric material. So if I say dielectric sphere or non-conducting sphere, what happens is the charge, once you put charge on it, it stays, it does not move. And it gets uniformly distributed, for now, all over the shape. So, this is a dielectric material. Somehow we put some charges in it. The charge will sit everywhere, on the surface, inside the material itself, because they are not free to move. They cannot move. And this is what distinguishes between insulator, dielectric, non-conducting, those are the same thing. Insulator and conducting material. In conducting material, charges are free to move. In non-conducting material, the charges cannot move.
In the non-conductor materials, they're moving from the surface into the sphere itself.
And the non-conducting? No, you put them, they stay there.
Even if they're close together and they can move out?
They cannot move. They cannot repel. This is the difference between non-conducting and conducting material. So but what happens if this is a cube, assume that this is a cube, conducting cube, aluminum, iron, copper, whatever, and all of us are electrons, all positive charges. And they put us inside that room. What happens? We all will try to move away from each other because there is a repulsive force between us, and we all will try to go at maximum distances from each other as we can. And this is only happen if we distribute ourselves on the outer surface of the room. I'll say it again. Okay? Because the medium will allow us to move freely. This is exactly what happens to the conductors. You put charge inside the conductor, any conducting material, they move out and they stay only on the outer surface. In non-conducting material, you put the charge inside, it stays there. Sometimes it gets distributed non-uniformly, and we'll study that. And sometimes they get distributed uniformly. And for simplicity, for now, I'm going to talk about uniform distribution. In the assignment, you'll find a problem about non-uniform distribution. And I'll teach you how to solve that.
But how are they non-uniform? Aren't there electrostatic forces?
Can I wait till we study chapter 25 and answer exactly what makes material different from electric point of view, what makes them insulator and what makes them conducting material? This is coming in chapter 25, so I don't want to jump into that. Okay, guys? Okay. You want a break? Okay, guys. Okay, so again going back to the lecture, this graph represents the electric field from a solid sphere that has a charge Q everywhere, inside the sphere and outside the sphere. Now let's assume that if you have a charge Q and you put it on a conductor, you have charge Q, and you put it inside solid conducting sphere, what happens? The charge will dissipate, away, will go away as far as much from each other, and they will reside only on the outer surface. And the inside the sphere, there will be no charge. That's a conducting solid sphere, conducting material, not non-conducting. What we have talked about a minute ago, this is non-conducting material. So, but if you have a sphere made of aluminum or copper or iron, any conducting material, and you put a charge on it, the charge will go and will stay only on the outer surface. Let's go back and calculate the electric field from a conducting solid sphere everywhere.
conducting ده they're not free to move.
No, the other way around. The other way around. Because they cannot leave the surface. Yes, so they are free to move, so they will repel each other till they go to as far as possible from each other, and this is only on the surface of the sphere. So if you have a solid sphere, that's a solid sphere, conducting sphere that has a charge Q. Charge Q. So the charge will go on the outer surface and will distribute itself. And the charge inside the sphere is going to be 0. Now let's guys calculate the electric field everywhere. Anyone want to lead that? Anyone want to actually to do this? I want to find the electric field at a distance or inside the sphere, then at a distance or outside the sphere. Okay, so what we do is the green, that's Gauss sphere. Because I'm going to do the inside first. Then write Gauss's law. ds or dA, sometimes I write it ds, sometimes I write it dA, so it's the area. ds equal to the charge inside Gauss's surface divided by epsilon 0. Before we go on, what is the charge inside Gauss's surface?
0.
Why 0? Because this is a conducting material and all the charge goes on the surface. So that means that E has to be, that's 1. This is E inside the sphere. Inside. شريف.
طب هو مش charge electric field بتاع طرف كل حته. يعني it will affect this surface.
Yes. And this is when you go in the Azhar tunnel, and if your radio is on, what happens is after some time you don't get any signal, because what happens actually, this signal is just an electromagnetic wave. This is our electromagnetic wave. So what happens is with this all iron mesh inside the concrete of that tunnel, the charge stays outside and it reflects that signal back, and it does not go in. That's why you do not get signal inside any tunnels. And mobile phone, they have to make some station inside the tunnel so they can get signal inside the tunnel. So this is E inside the sphere. How about E outside the sphere? I want to find the electric field at a distance R outside the sphere, that distance. We need to find the electric field at that point. Someone was asking about where to draw Gauss's surface. So if we need to find the electric field at that point, we draw Gauss's surface at that point. So here again, this is the green sphere. This is my new Gauss surface. Let me finish that proof, then I will answer you. Now let's find the electric field. Let's find the electric field on that surface. Again, we write Gauss's law. E on Gauss's surface is constant. It goes out of the integration. The integration over dA, that's the area of Gauss's sphere. How about the dot product? The area and E are along the same direction, so the angle between them is 0, so the dot product will give you 1. Equal to, what is the charge inside Gauss's surface? total charge Q. So again, the electric field will equal to 1 over 4 pi epsilon 0 Q over R squared. This is the same as non-conducting sphere. So again, for conducting sphere, for conducting solid sphere, the electric field outside of the sphere will look like as if the charge is concentrated in the center. It will look like as if the charge is concentrated in the center. As if it's a point charge, as if it is a point charge. Sharif.
كنت عايز اقول ان الار مش كلها بنستخدمها صح؟ يعني المفروض تبقى الار الريديوس بتاع جاوس سيرفيس كبيره ماينس الريديوس.
No. You measure R from the center of the sphere, from the origin. Or, you know, if you remember, when we wanted to measure any displacement or a position of anything, you need to choose an origin, right? Right? So if you remember from the physics 111 first two classes, we said that I'm going to choose that corner of the room to be my origin. And this is X, this is Y, and this is Z. Same thing goes in here. We have to choose a coordinate system. So I choose that to be an origin. The reason that I choose that to be an origin, to be my origin, is to have a symmetry. If you choose that point to be your origin, there will be no symmetry. So I choose that to have the symmetry. And we need the symmetry to apply Gauss's law. Without Gauss's law, without symmetry, you cannot apply Gauss's law. Okay? Because if this is your origin, then you want to draw Gauss's surface around it. The charge inside Gauss's surface will not be symmetric. Okay? Okay. What else? Guys, what else? Yes.
Why does it appear to be like a point charge?
It is a point. It looks like if it is a point charge.
Why?
Oh, the reason, physical reason?
Yeah.
Okay. What you're doing really here is you're averaging, you're getting the electric field from each component in here. And by symmetry, again, the electric field from that component at that point is going to be strong, while the electric field from that part at that point will be a little bit weaker. But it will be, if you take the same distance at the other side, you will get the same exact answer. So it will look as if it is the charge is concentrated exactly in the center, because you're actually getting an integration. What we are supposed to do is to apply Coulomb's law. By the way, before we go on, Gauss's law is just an approximation. It only works if we have symmetry. But Coulomb's law, this is the exact law. It works for any shape. Okay? So that's why you're getting integration all over the sphere.
What do you mean by symmetry in this case?
We have we have three kinds of symmetry in this course. We have cylindrical symmetry, so any shape that has a shape of cylinder, a wire has a shape of a cylinder, then you can choose around it Gauss's surface to be a cylinder. Any shape that has a shape, any shape that has a spherical shape, then you can choose Gauss's surface to be around it as a sphere. Planar symmetry, then you can choose a cube. So if we have a plane that has a charge, I can choose either a cylinder or a cube to be my Gauss surface, and we'll study that part on Monday. So what I mean by symmetry, that if you stop in the middle in here and you look around you, everything will look exactly the same.
I mean, there's no symmetry in the point that shows outside the sphere.
Oh, but in the center. If you are on the origin, everything will look exactly the same. So if I stand in the middle of that room, do I have a symmetry? not spherical. If I look around me, every point will not look the same. But I have mirror symmetry. This is a mirror of that, and this is a mirror of that. So if you look to the right and the left, you find that those two walls, they look alike, as if one of them is a mirror for the other one. If you stand here and look to the right and the left, they will look as if the two walls are mirror from each other. So, and if you have a cylinder, and you stand in the middle of the cylinder and you look around you, everything will look exactly the same. If you have a sphere, and you stand inside in the origin of that sphere, in the center of the sphere, you look around you, everything will look exactly the same. This is what I mean in a simple way by symmetry. Excuse me? Planar symmetry, planar symmetry, and we'll get into that. Yes, in a planar symmetry, if you have a plane, and if it has a charge Q, and you need to find the electric field everywhere from that plane, then you have to choose Gauss' surface. And the choice of Gauss' surface in here, you can choose either a cylinder or a cube. A cylinder or a cube, and I'll teach you how to do it. Okay, guys? Okay? Can I take 5 more minutes? 5 more minutes. So now let's assume that we have this complicated shape. We have in the center a sphere. Now we're going to use the right terminology from now on. Guys, in the center we have a sphere, a solid non-conducting sphere that has a negative charge, negative 3 microcoulombs. A micro is equal to 1 times 10 to the power minus 6 of anything. So when I say microcoulombs, that means that that's minus 3 times 10 to the power minus 6 coulombs. So that's in the center. And around it, there's a spherical shell. And that spherical shell does not have any charges on it. That spherical shell does not have any charges on it. No, this is only one. Then gap, air, vacuum, air, in here, look at the arrow. Then you have another shell, spherical shell, that has, that does not have any charges.
And the distance in between is
This distance is vacuum.
It's not sphere, it's not
It's not a shell. This distance in between them is not is a vacuum, is air. And this is a spherical shell, this is a spherical shell, and this is a solid sphere, non-conducting sphere. When I say non-conducting sphere, what does that mean? The charge is distributed everywhere. When I say non-conducting sphere or insulating sphere or dielectric sphere, I mean that the charge is distributed everywhere, inside and out and on the surface of the sphere.
Now conducting is our surface.
If it's conducting sphere, then the charge is only on the outer surface, and we'll see it. We'll prove it. Now, we need to find a solid non-conducting sphere carries a total charge of negative 3 microcoulombs, distributed uniformly throughout. It's surrounded by an uncharged conducting spherical shell. So we have around a metallic spherical shell. This is case A. Case B, it's exactly like case B. So we have another case, another geometry, but the spherical shell is removed. So we have only the sphere. So you have a sphere, this is the case B, and the sphere are surrounded by a conducting shell, this is case A. So those are the two cases. Now, we need to compare the electric field at point X. You see where is point X, which is outside that whole thing for the two cases, A and B. we have EA is less than EB, EA equal to EB, EA is more than EB. A, B, B, ممدوح. Why is it B? Okay, by the way, in the exam, if you give me an answer and you do not explain, it's exactly as if you don't answer it.
دكتور
Yeah.
هي ممكن في حاجه واحده تفرق بس اللي هي الابسن دي بتاعت الشلل.
Let's think about it. Let's think about it. Let's think about the physics. What's going to happen? You have a charge Q, negative charge Q, negative charge Q, and you bring something closer to it. What's going to happen in here? If this has a charge positive Q, what's going to happen in that inner surface? You get a negative charge, same amount of the charge on the inner surface, right? And on the outer surface, you get positive. Forget the problem for now. Again, you have a charge Q, positive Q here, here, charge positive Q here. Then you get around it and you put a concentric shell. So in the inner surface of the shell, the positive charge, the shell has the equal amount of positive and negative charges. You have now an equal amount of positive and negative charges. Any material has an equal amount of equal and positive and negative charges. So when you bring a positive, when you put a positive charge in the center, it will attract negative charges to it. So in here on that shape, the negative charge will come closer to the positive, and the positive will get far away. They will be repelled by the positive charges. So on that shell, in the inner surface, you get negative charges, and on the outer surface, you get positive charges. Same amount, of course. Same amount of charges. Okay. So now what happens in here, in case 1? You get in that surface positive Q, and you get on that surface negative Q. What is the total charge inside Gauss's surface?
Total charge is negative Q.
Negative Q.
ناخد into consideration R.
Forget about R for now. Forget about R for now. We'll do it.
What does that mean exactly?
This is the sphere that has negative Q, and this is the spherical shell. So in that surface, you get positive Q, and that surface you get negative Q, correct? And we need to find the electric field at that point. So what to do? We draw Gauss's surface, a green surface, virtual surface. Oh, here it is. Then you write Gauss's law. That means that E times 4 pi r square equal to Q inside Gauss's surface. What is the Q inside Gauss's surface? It's this plus that plus that. No, it's negative Q plus Q. 0 plus negative Q, so it's negative Q over epsilon 0. You end up having E will equal to 1 over 4 pi epsilon 0 Q over r square, and you have a negative sign here. So that's case A. Case B, it's exactly the same. It's going to be exactly the same. If you look, if you remove that part, the shell, and you look inside Gauss's surface, what is the charge inside Gauss's surface? The distance is the same, R is the same, Q is the same, so the electric field should be the same.
Doctor, what the difference between this example والtunnel example? عشان حضرتك قلت ان tunnel example it will
The electromagnetic wave come and charge that with some charges, so it will actually reflect that electromagnetic wave away after sometimes. But here you have, from the beginning, we have put some charged particle inside.
And you, doctor, you said,
We put a charged particle. This is totally different. This is not the case.
doctor, you said this is not conducting.
Which one of them?
This is the example.
Which one of them? This, the shell, or the sphere?
The sphere itself.
Yeah, the sphere is non-conducting. Is non-conducting. While the shell is conducting.
So what's the difference? الضوء لو كانت السفير
That's not the problem now. I'm not going to answer that. I'm not going to answer what if. What if that was a conducting in the center? Nothing is going to be different. It's going to be exactly the same. Not everything is going to be the same. The electric field at that point is going to be exactly the same.
So كان في one shell بس كان electric field على zero.
It's only one shell.
نعم.
It's only one shell. No. No. Guys, please concentrate. It's only one shell. Again, we have a sphere. We have a sphere, solid sphere,
Okay.
then vacuum,
Okay.
then shell. This is a shell that has a thickness.
Oh, okay.
Okay? Ala said, okay, if this was a conducting sphere, will the electric field be here, will be the same? Yes. How about the electric field inside that sphere? The electric field inside that sphere, it's going to be different. If it's conducting or non-conducting. If it's non-conducting, we will have some electric field inside, in here. We'll have some electric field. If it's conducting, the electric field inside is going to be zero. That's what we have proven a minute ago. Ala.
What if the spherical shell is non-conducting?
What if the spherical shell is non-conducting? So what's going to happen?
non-conducting يبقى the electric field zero
Okay, Ala.
outside.
If the spherical shell is non-conducting, is conducting first, which is the case, the electric field inside the shell is going to be zero. If it's non-conducting, the electric field is not going to be zero. And all those problems, we're going to solve them. I have finished chapter 24, last lecture, when I stated Gauss's law. That was everything in chapter 24. What we're doing now is we are studying so many examples, that's all. So we're going to study that. It's going to be either in the coming lecture or in the assignment.
After if we remove the vacuum, we have the sphere and the shell moved.
And how are you? So they will collapse to each other? What do you mean? There will be no distance between them?
No. And we have the sphere itself,
The sphere, here is the sphere.
yes, and then the shell.
And what's between them? What are you going to put between them? Here is the sphere and there is the shell. How do you want to put them? It has to have there's a gap between them. You can fill that gap by anything. Air, vacuum, water, jelly, anything. What else?
ايوه طب لو نون كوندكتنج سبيريكال شيل او نون كوندكتنج ايه اللي هيبقى الالكتريك فيلد على كل ده هو
Yes. All what matters is what is the charge inside Gauss's surface.
بالتالي الالكتريك فيلد هيبقى ثرو
The non-conducting, it will. That's much easier. The electric field goes through non-conducting material, but it does not go through a conducting material. The electric field from that charge, it's isolated from outside, guys. What happens is that negative Q have created here a positive charge Q and a negative charge Q. And the electric field that you see is from that charge. And it will look like as if it's all concentrated in the center. I'll say that again. This is very important. That negative charge Q have created here a positive charge Q. And on that outer surface, it created a negative charge Q. And the electric field that you see outside is due to that negative charge Q. And it will look as if it is all concentrated in the center. That's what we have studied in the example that's before that.
هي ليه نيجاتيف charge non conducting ده هتستخدم
Which one is non-conducting?
outer
Guys, you're confusing yourself now. You're really confusing yourself. Do you understand that problem? So anyone wants to actually assume anything, just put it in a paper, come to me, I will solve it with you. Okay? And we can later on scan them, all of those, and put them on blackboard. Think of any arrangement you want and try to solve it. And if you cannot solve it, come to me, I will solve it with you, we'll scan them, Franz Henny will scan them for us, we'll put them on blackboard. Okay? But it's doable. But if we keep saying what if, most of the people will get confused. You understand that one? Yes. Whatever you want to think of, try to solve it. If you cannot, please come to me, I will solve it with you and we'll actually distribute it for the whole class. Yes.
حواليه هنا النيجاتيف اللي جوه عامله بوزيتيف هنتكلم عليه.
If you have a positive charge, positive charge will try to attract a negative charge. Everything wants to be neutral. Everything. So if you have a positive charge and that material is neutral, so it will try to attract the negative charges in here to it. So the negative charges will move to that surface and they will stop because there is no way that they can cross that gap. So they will stop. That surface will be negatively charged and that surface will be positively charged. Okay. But the total surface will stay neutral. Yes. And we call that, if you remember the first lecture, polarization. Okay guys, should I stop here? Okay, I'll stop here and I'll see you on Monday. B. Oh. Okay. B. Sorry. What is the surface charge density sigma 1 on the inner surface of the conducting shell in case A? So in that case, what is the surface charge density? What is the definition of surface charge density? It's the amount of charge divided by the surface area. So the surface area of the inner surface is 4 by r square. Whatever the r of that inner surface is, r1 square. What is the charge on the inner surface? Q1. So the sigma 1, that sigma is going to be Q1 positive divided by 4 by r squared. So which one is going to be the answer? More than 0, of course. Oh. Would you like to answer that? Yes. Yes, what's your name again? Ghad is saying, because you have a positive charge. Yeah. Okay, good. What else? No, they want the surface charge density. The surface charge density. Q. Green. Yeah, on the shell, on the inner shell. So the charge on that shell divided by the area. That's it. Yeah. Okay, guys. Thank you for coming. I'll see you on Monday. Unless you want to come and see me for anything on Sunday.